Per protocol, efficacy amplification coefficient refers to the mathematical divergence in clinical endpoints observed when comparing intention-to-treat datasets with fully adherent subjects. In free-living comparative clinical nutrition, calculating this value quantifies the true biochemical potency of a metabolic matrix, isolating its physiological capacity from the behavioral and environmental friction factors that drive population-wide compliance decay. To evaluate the long-term metabolic outcomes of self-selected lifestyle interventions under free-living conditions, a comprehensive breakdown of the 12-month clinical dataset from the University of Otago trial is required. This exploratory secondary analysis tracked 250 adult human subjects exhibiting an aggregate baseline mean age of 48.2 years and an aggregate baseline mean body mass index of 32.3 kilograms per meter squared. The structural framework of this clinical design deliberately bypassed investigator-led randomization, granting the participant cohort absolute autonomy to self-select their primary intervention based on individual behavioral preference. The subjects selected between three distinct dietary methodologies: a 5:2 intermittent fasting schedule, a modified Paleolithic diet, or a whole food Mediterranean diet pattern. Simultaneously, they selected their physical activity track, choosing between standard moderate intensity physical activity guidelines or unsupervised high-intensity interval training, known as HIIT. Following their initial selection, participants attended a single, solitary 30-minute lifestyle counseling session with a registered dietitian or exercise specialist to establish baseline nutritional parameters. No meal delivery services, financial incentives, or ongoing clinical accountability check-ins were provided across the subsequent 12-month duration. This design allowed investigators to map the precise behavioral compliance decay curves that occur when autonomous populations operate within standard modern obesogenic environments. The baseline enrollment metrics exposed distinct population-wide preferences. The 5:2 intermittent fasting arm was heavily favored, selected by 136 individuals, representing 54.4% of the entire participant pool. The Mediterranean diet pattern was chosen by 68 individuals, capturing 27.2% of the cohort, while the modified Paleolithic model was the least popular option, selected by 46 individuals, representing 18.4% of the total population. The baseline physiological metrics across all three self-selected groups showed no statistically significant differences prior to day one of the intervention. The initial aggregate cohort exhibited a mean body weight of 94.9 kilograms, an average systolic blood pressure of 128 millimeters of mercury, an average diastolic blood pressure of 82 millimeters of mercury, and a mean baseline glycated hemoglobin concentration, or HbA1c, of 35.8 millimoles per mole. As the trial progressed into the long-term 12-month timeline, the primary behavioral endpoint shifted to tracking self-reported dietary retention. The data revealed a steep, progressive attrition curve across all three arms, illustrating the severe psychological and social friction of sustaining long-term restrictive eating patterns without continuous supervision. By month 12, the Mediterranean diet pattern proved to be the most behaviorally sustainable model, maintaining a self-reported retention rate of 57.4%. Intermittent fasting tracked closely behind, with 54.4% of its original choosers remaining adherent. Conversely, the modified Paleolithic framework suffered an extreme behavioral collapse, with its retention rate plummeting to just 35% by the conclusion of the one-year evaluation period. The operational divergence in these behavioral trajectories is directly tied to the precise macronutritional boundaries and structural constraints of the three self-selected interventions. The 5:2 intermittent fasting protocol imposed an intense, nonlinear energy restriction, requiring participants to severely limit their energy intake on 2 non-consecutive days per week, while allowing unconstrained eating to satiety on the remaining 5 days. On these 2 fast days, female participants were restricted to a maximum of 500 kilocalories, and male participants were restricted to 600 kilocalories, typically consisting of a single nutrient-dense meal composed of lean proteins and low-glycemic vegetables. The modified Paleolithic diet demanded a massive evolutionary shift in food selection. It required the complete exclusion of all cereal grains, legumes, dairy products, and ultra-processed foods, forcing participants to rely entirely on minimally processed lean meats, poultry, fish, eggs, nuts, seeds, and non-starchy vegetables. However, to reflect a more realistic real-world scenario, the Otago researchers allowed up to one daily serving of either legumes or a grain-based food item. Though even with this modification, the strict exclusion of entire food groups generated immense long-term culinary friction. The Mediterranean diet structure focused on the systemic incorporation of healthy fats and whole food groups rather than rigid restriction. Red meat was strictly minimized, limited to less than one serving per week, while processed meats and refined sugars were completely discouraged. When analyzing the objective physical endpoints through a strict intention-to-treat statistical lens, which includes every participant who originally selected a diet, regardless of whether they dropped out, the 12-month weight loss outcomes revealed distinct differences across the cohorts. The 5-2 intermittent fasting protocol generated the highest absolute mass reduction, achieving a mean weight loss of 4.0 kilograms over the one-year duration, with a 95% confidence interval ranging from -5.1 to -2.8 kilograms. The Mediterranean diet pattern demonstrated a stable, intermediate weight loss trajectory, yielding an average reduction of 2.8 kilograms at the 12-month mark, with a 95% confidence interval ranging from -4.4 to -1.2 kilograms. The modified Paleolithic group produced the least effective long-term outcome, dropping an average of only 1.8 kilograms over the course of the year, with a 95% confidence interval ranging from -4.0 to +0.5 kilograms. Because the statistical confidence interval for the Paleolithic cohort crossed zero, the data indicates that when evaluated on a population-wide intention-to-treat basis, the Paleolithic model failed to produce a statistically significant long-term reduction in body mass. Because real-world weight loss trials are deeply affected by participant dropout, the Otago investigators executed a series of sophisticated sensitivity analyses to correct for missing data points and prevent over-optimism. When applying a multiple imputation model to simulate the trajectory of dropouts assuming they returned to their baseline weights, the adjusted intention-to-treat figures became slightly more conservative. The imputed weight loss numbers dropped to a mean of 3.1 kilograms for the intermittent fasting group, 2.1 kilograms for the Mediterranean cohort, and a negligible 0.8 kilograms for the Paleolithic arm. However, when the data analysis shifted focus to look exclusively at the per-protocol population, isolating only those dedicated individuals who remained fully compliant and strictly adherent to their chosen diets for the entire 12-month duration, the true physiological efficacy of these nutritional matrices became profoundly amplified. Among the participants who maintained absolute, verified adherence to the 5:2 intermittent fasting protocol for the full year, the mean weight loss expanded significantly, yielding an additional loss of 1.1 kilograms over the baseline group average. For the fully adherent Mediterranean subgroup, the metabolic impact was even more pronounced, generating an additional average weight loss of 1.8 kilograms, which brought their true 12-month per-protocol mass reduction to a robust 4.6 kilograms. In stark contrast, even among the highly disciplined minority who managed to remain strictly compliant with the restrictive Paleolithic guidelines, the per-protocol analysis yielded an incredibly disappointing addition of only 0.3 kilograms of weight loss. This critical data point demonstrates that the radical elimination of whole grains and dairy foods provided absolutely no additional metabolic or thermodynamic advantage for long-term fat mass reduction when compared to the far more sustainable, inclusive whole food choices of the Mediterranean model. Beyond basic measurements of total body weight, the secondary analysis tracked several key biomarkers that dictate long-term cardiovascular health, endothelial function, and metabolic longevity. Distinct improvements in vascular tension were recorded across both the intermittent fasting and Mediterranean diet cohorts. Over the 12-month timeline, the intermittent fasting group achieved a mean reduction in systolic blood pressure of 4.9 millimeters of mercury and a reduction in diastolic pressure of 2.6 millimeters of mercury. The Mediterranean cohort demonstrated an even more impressive vascular stabilization, dropping their average systolic pressure by 5.9 millimeters of mercury and their diastolic pressure by 3.0 millimeters of mercury. This steady, sustained drop in hydrostatic pressure reduces long-term endothelial shear stress, directly lowering the probability of vascular wall injury and subsequent atherogenic plaque initiation. The Paleolithic group failed to show any meaningful alterations in blood pressure metrics, matching their poor compliance scores. The most clinically significant divergence between the interventions emerged within the parameters of long-term glycemic regulation, which was quantified via changes in plasma glycated hemoglobin, or HbA1c, concentrations. The whole food Mediterranean diet pattern stood out as the only lifestyle intervention in the entire trial capable of driving a statistically significant reduction in glycated hemoglobin, achieving a mean drop of 0.8 millimoles per mole over the 12-month observation period. This systemic reduction in HbA1c represents a meaningful downregulation of advanced glycation end products and a clear enhancement of peripheral insulin sensitivity. This outcome was driven by the steady, daily influx of dietary fiber, polyphenol compounds, and monounsaturated fatty acids, which optimize cellular membrane fluidity and glucose transporter kinetics. Strikingly, despite achieving the highest absolute total weight loss, the intermittent fasting group completely failed to mirror these glycemic improvements, showing an insignificant change in their HbA1c levels, which indicates that periodic severe caloric restriction without high dietary quality may not optimize glucose handling as effectively as a sustained whole food matrix. The simultaneous evaluation of the exercise arms in the Otago trial revealed a behavioral pattern that perfectly mirrored the dietary arms. At the beginning of the study, high-intensity interval training, or HIIT, was highly popular among participants looking to maximize their exercise efficiency. However, without continuous clinical supervision or group class accountability, long-term compliance collapsed. By the 12-month mark, the proportion of participants who managed to consistently complete at least 2 unsupervised HIIT sessions per week fell to a mere 19.6%. Yet, the small minority of individuals who did maintain strict compliance to the HIIT protocol experienced substantial, disproportionate metabolic rewards. These adherent individuals achieved significant, independent reductions in both total body weight and visceral adipose tissue volume compared to those performing standard moderate-intensity physical activity, proving that high-intensity protocols possess massive fat-burning and metabolic clearing power, provided an individual can overcome the heavy behavioral barriers to long-term compliance. For an individual attempting to transition from a long-term low-carbohydrate or Paleolithic framework to a carbohydrate-inclusive Mediterranean model based on these data vectors, a highly controlled step-by-step approach is mandatory to avoid metabolic distress. A sudden, uncontrolled influx of carbohydrates into a system downregulated for glucose metabolism can trigger acute glycemic spikes, reactive hyperinsulinemia, and a profound shift in fluid dynamics driven by glycogen-associated hydration kinetics. Because every single gram of stored cellular glycogen chemically binds and retains approximately 3 to 4 grams of water, a sudden shift in macronutrient ratios causes a rapid expansion of intracellular and extracellular fluid volume, simulating rapid mass gain that is independent of adiposity. To prevent this fluid surge and ease peripheral tissues back into optimal insulin sensitivity, the transition must be executed through a systematic phase-in protocol over a minimum timeline of 4 to 6 weeks, slowly stepping up intake by exactly 10 to 20 grams of high-quality complex carbohydrates per week, utilizing lentils, chickpeas, and ancient grains. Saturated fatty acids must be surgically replaced with monounsaturated fatty acids, with cold-pressed extra virgin olive oil serving as the primary culinary fat, averaging 2 to 3 tablespoons per day, while animal protein sources are scaled back to minimize red meat to once a week or less, exactly as outlined in the successful Mediterranean arm of the trial, ensuring life-extending metabolic improvements are locked in permanently.